class, we are going to talk about sterilization in more detail, and we'll talk about this topic in two lectures. The first one is more like a review or overview of the sterilization, the purpose, definition, and the second one will be more focusing on the calculation. Okay, so the learning outcomes from today's class first will be describing the purpose and principle of sterilization process, which is more like a recall or refreshment. And then we'll talk about the bacteria, what are the key factors might affect their survival and growth in foods. And third will be discussing some key factors that we have to consider during sterilization process, and also identify some heat transfer types and code for point. I decided to add this part because last time when we were going through the thermal processing principle, I noticed some of you were not quite familiar about this. So I decided to quickly bring that up here so you guys can, for those of you who didn't have much idea about this topic, you can probably have a better idea after this class. And also we'll compare different retort systems. And finally, we'll briefly go through the lab tomorrow. So it's it's also about sterilization, and we will have 4 groups working on 4 different treatments. So we'll briefly talk about that. And also I'll upload a handout of the tomorrow's lab after today's class. Okay, so in case you haven't downloaded this slide from the Canvas, please do so you can take notes. Okay, I just uploaded about like 7:50 in the morning. Okay, so this is about the sterilization 1, which is more like a concept review. And our next lecture on the Tuesday next week will be more about calculation. So it'll be more rigorous in calculation about how to estimate the processing time. For example, if you are asked to inactivate the Clostridium botulinum with a given F value, for example, 3 minutes, how long do you want to process it? So basically we have to analyze the heating curve and calculate all the parameters like come up time, thermal lag factor, heating rate constant, cooling lag factor, and use all those parameters to calculate the processing time, the estimation, right? And we will also use the data from Friday's lab because we'll collect some data tomorrow, and on next week we'll use the data collected from tomorrow's lab to do all those calculations. Okay. Okay, sounds good. So first, I want to briefly talk about food processing, thermal treatment. If we look at that, whatever we have covered in past lectures, blanching, pasteurization, and sterilization, their heating, the degree of heating are all quite different, right? So blanching and pasteurization are more mild, but sterilization is more intense. So regardless of mild or intense process, the goal, it's always a balance between food quality and safety, right? So for blanching and pasteurization, we apply a very mild heat to ensure the food quality and without too much of food safety. So the goal is more to retain the food quality, right? So, but we have to store them in refrigeration or freezing. So that's something that it's compromising. But in sterilization, the goal is to keep the food as long as we can on the room temperature, right? But in that case, we are sacrificing the quality. So it's always the dilemma in food processing, and we always want to, depending on the requirement of the storage and processing, we have to decide the best practice to ensure the safety while maintaining the flavor, the sensory, the texture, or the food quality properties. So that's about the principle of the thermal processing. So first of all, I want to identify the problem of the microorganism. Although we are already in 21st century, but the food safety is still a bigger problem in the United States. For example, in 2020, we have seen more than thousands of cases in those foodborne illness. For example, Campylobacter, Salmonella, E. coli, and Listeria, they're always the troublemakers. Okay, and even recently, after 20 years after that, we still had a lot of recalls and outbreaks related to Listeria, Salmonella, those strains we have been dealing with for hundreds of years. And one example that I want to mention to you that those foodborne illness, they do not necessarily cause hospitality or death, but they do cause a tremendous economic loss. One example is that in 1997, so probably you guys were either not born or either very young, like a infant. But in 1997, there was one company called Hudson Foods in Arkansas, and they had a problem with the E. coli contamination in their beef. And initially, once the problem was identified, they recorded 20,000 pounds. But later on, that number increased to 1.2 million pounds and finally ended up with 25 million pounds. And the 25 million pounds, if you multiply the price by the price of beef, that's millions of dollars. And it's almost like 1 year's revenue of a food company. So that company went bankruptcy and was sold eventually. So the problem of those recalls, their economic loss is more, it's just very considerable. So the reason that even with now, the companies are always using the same standard protocol to process foods, but we still have a lot of those issues. It's because those microorganisms or pathogens, they have different tolerance under different environment. For example, one of the biggest factor is the water activity. So here I listed 3 microorganisms. Their F value under moist heat and dry heat. So basically, you can understand it as high water activity and a low water activity. So if we have the Bacillus polymaxa in the high water activity foods, we only need 0.01 minute. You see the F value 0.10 minute to kill the pathogens. And the Z value is 14 degree F, which means it's highly sensitive to the thermal treatment. But however, if the water activity drops, then we need 6,700 minutes to kill this pathogen. And the Z value also goes up to 26 degree F. So that's why that when we are processing the food, the water activity change in food. For example, if we forgot to close the lid appropriately, then cause the evaporation of the water before gets retorted, and then we might have this kind of issue because the water activity drops, then we essentially need more time to process it, but we're still following the standard protocol, then those pathogens will cause issue. So that's one of the biggest issues, the water activity. And the second one is the pH or the acidity. So we already learned from the previous lecture that our previous classes that we have three categories: foods, low acid foods, medium acid, and high acid foods. Right? So the cutoff pH is 4.5. For example, in low acid foods, we have meat products, fish, dairy products, and vegetables. And in medium acid foods, we have a lot of fruits, right? And the high acid foods, they're more like pickles, citrus, and cranberry juice. And we know that in those low acid foods, there's more concern about pathogen. For example, Clostridium botulinum only grows in the low acid foods, right? It's always one of the biggest concerns to canned foods. But in high acid foods, we do not have any more of those pathogen concern, right? But we still have a lot of spoilage organisms. Um, for example, because we know that Clostridium botulinum, they have high resistance against those spoilage organisms. So we have to identify. So when we're processing high acid foods, we have to identify what are the target microorganisms, and depending on that, will determine our processing time. Okay. So I'm going very quick on those topics because I assume that you have learned about it in previous courses. So in case that you want me to slow down, please raise your hand or let me know in the chat box so I can, talk a little bit slower. So this is how we determine the processing time for the targeting microorganism. For example, the Clostridium botulinum, if we plot out the thermal death time, which is the F value against the temperature, we'll get a straight line. Okay, so but remember the TDT, the thermal death time, is plotted out in the log semi-log plot, right? So everything on this line will be able to reach a 12D reduction. So if we're doing retort, which is usually 250 degree F, then we can find our processing time is close to 2.45 minutes. So that's the F0 value, which is the standard F value that we have to refer to. Okay, so canning process. So once we know the F0 value, we can start designing our canning process, right? So typically we start with fill the foods into the cans and seal. Sometimes we use vacuum to avoid the oxygen in the headspace, because under those very high temperature, the lipid oxidation and a lot of other oxidation reaction will be accelerated. So sometimes we use nitrogen to seal, and sometimes we even use a vacuum to pull off those air. And then after sealing, we will place the can into the retort, okay? And then apply, increase the temperature using steam, right? So once the system is running, the temperature of the system will be gradually brought up to the standard temperature, which is close to 250. And the time that the temperature is ramping, we call it come up time, or CUT. And then afterwards, we will maintain the temperature at that standard operation temperature for a required time. And finally, we'll cool down the can quickly after the time is reached using water, typically water. And the surface will quickly dry because it's the temperature very high. And afterwards, we'll label it, right? So there are a lot of factors that might impact the our canning process, right? So here I want you guys to discuss So here I listed about 8 factors that I think about, and I will put you guys into 8 breakout rooms. So each of you will discuss the impact of these factors in different food processing and in how they are impacting the retort time. Well, let's do this way. So since we have 8 factors, I will divide you into 8 groups. Like, okay, so like group 1, team 1 will you guys will talk about the apparent viscosity, how that will impact the retort time. Okay, so group 2 will talk about the can size. Okay, and group 3 will think about how the type of product will impact the retort time. And group 4 will discussing about rotation speed, okay? And the group 5 will talk about the retort temperature and then headspace. This is a very tough discussion, okay? Headspace, it might be a little bit difficult. And then group 7, you guys will talk about ratio to the liquid to particle ratio, okay? And group 8 will think about what package we use. For example, if we're using pouch processing or if we use can packaging, how will that impact the retort time? So let me put you guys into those breakout rooms, and I'll give you about 5 minutes. So once you come back, I will check with each group and then see what you guys think about, okay? And afterwards, don't worry if you cannot get this the good answer, because afterwards we'll go through each factor and discuss about them, okay? Okay, so I'm opening 8 groups, and guys can go in all rooms. Okay, so we have everyone back. Okay. All right, so let's start with group one. Other groups, if you have something to add, you guys can raise your hand or just unmute yourself. So let's start from group one. So what do you think about um, the apparent viscosity might impact the retort time? So I have Armin, Lauren, Paris, and Sophia.
Yeah, we just talked about if the viscosity is higher,
Mm-hmm.
it's going to be, the retort time is going to be higher. And if the viscosity is lower, the time is going to be lower. So that's basically what we talked about.
Yes, it sounds very straightforward, right? And so have you guys think about if you are processing it in steel retort and rotary retort, which one has more better impact on the viscosity? For example, if you are processing the highly viscous foods in a steel retort, do you think versus a non-viscous food in the steel retort, do you think which one has bigger gap that you have to, which type of retort that you have considered the viscosity more?
Oh, are you asking like which is going to be better, like rotary versus steel?
Um, okay, let me explain. Let me think. Saying this way. So we know that in steel retort, the viscosity might be a huge issue, right? Because you don't have too much convection there, right? And everything is only done by conduction. But in steel retort, the viscosity, if you have high viscosity, then the convection is inhibited. But we kind of added some agitation to overcome that viscosity problem, right? So so in that case, the gap between the viscous and the non-viscous food in steel retort, their processing, their heat penetration might be less prominent compared to the steel retort, right? So this is something that I wanted to ask. Okay. All right. Any other groups? Did you guys have want to add up something to the viscosity topic?
We
No.
talked a little bit about like this. I mentioned like the center, essentially like the cold point. So if it's more of like a viscous food or thicker, that cold point's going to be harder to um, get to reach the surrounding environment. And then if it's less viscous or if it's being, agitated, that cold point would be a lot easier to raise the temperature of.
Good point. Good point. Excellent. So good job, Arma and Paris. Good job, Group One. So let's move to Group Two. So Group Two will we have Abby, Chloe, Emmy, and Yvonne. So how about can sites, guys?
So we talked about the can size.
Mm-hmm.
The smaller the can size, the smaller the time, because the temperature can penetrate to the middle of the can or the cold point, as Paris mentioned, quicker. A larger can, you would have more product to heat within the can, so more thermal differences. So you'd have to,
yeah,
account for that.
Yeah, good job, Abby. So let me ask a question. So if you, because if you are processing a bigger can, then apparently you have more higher production capacity, right? But if you're processing a smaller can, the residence time is shorter, but the capacity of production also drops. So how would you find the optimal point about the can size selection?
I think you have to look at the cans over time or the product over time and the price for those cans. So I think, yeah, bigger cans, you might be able to process more product, but are you getting that value for that product because it's in a bigger can? Normally it's a cheaper per ounce. So yeah, you also have to take that into account. I don't know.
That's a good answer. Okay, so any other thoughts?
I was also curious about the can like shape. So would a shorter, fatter can or like be more effective than like a skinnier but taller can? But then you have more, like if you're stacking the cans, how does that play a role?
Yeah, the candle shape, exactly. I think to my understanding, the tall can and the skinner can, the heat penetration should be more efficient, right? Because think about it, if you are heating up a cubic shape, then the center is located further from the surface. But if you have a very thin side, then the center, it might be just a few fingers from the surface, right? So to my understanding, a tall can, in terms of heat penetration, should behave better, right? Okay, good job, guys. So group 3, you guys have Adriana, Carlisle, Jared, and the chemical. So what about type of product, guys?
So we just kind of talked about also, I mean, the viscosity of what the product is going to have, and also if it's a low acid or medium acid or high acid, or what the pH on the food would be, because that's all dependent on it. One of the questions that we had was like accounting for a carbohydrate in the retort, because obviously, like if you're making a Chef Boyardee product which has tomato sauce and pasta in it versus just like a can of tomato soup, we were just kind of wondering about where a carbohydrate would factor in with like extra time.
That's a good question. Well, any thoughts from you guys? Maybe a guess.
All I can think of is like, right, like carbohydrates would therefore like increase your viscosity likely. And so that would just go along with that. It's like if you have a thicker product. I think in like my group, not to like jump the gun, but like we talked about like solids and liquids. So like in the Chef Boyardee example, right, you have like sauce and chunks of pasta. And so obviously that would like make it more difficult.
Yeah. Yeah, that's a good answer, Julia. Yeah, that's pretty much what I thought. So carbohydrates, depending on what type of carbohydrates, whether starch or sugar. So apparently they will impact the viscosity and the water activity, and they might affect how the bacteria tolerate the heat, and also how the heat penetration. It's going to be complex if you think about this problem. Okay. So group 4, you guys talk about rotation speed. So that's all mostly related to the Rotary retort, right? So guys, what about we have? Let me see. We have Justin, Kristen, and Maddie.
Yeah, so we talked about how faster rotation speeds will reduce processing time and will also help eliminate any cold spots in the product.
Yes. So can we go very fast? Like if you want to go fast, how fast you want to go? Can you go like a fan size speed? No, I saw Julia not shaking the hand. So what speed do you think is a good speed? How to determine that? Well, that might be a tough question. And honestly, I don't know the answer. Probably we have to run a few trials and see what is the minimal speed. For example, later on, actually, I will show you a few plots about how the rotary, the rotation speed impact the F value. And actually, there is a certain critical speed, which means before the speed, once you increase the speed from 0 to that number, you can reduce the processing time. But after that speed, the reduction of time becomes not significant. And probably, I guess we can simply stop increasing speed at that value so that we can save some energy, because the right, so that's my thought. It's not mature thought. I'm not sure if you guys have better thoughts. If you I will let you guys discuss more after we have done with the Rotary, the Rotary retort experiment next week. Probably you guys have a better idea then. Okay, number 5 is the Rotary retort temperature, and we have Chris, Georgia, and Veronica.
So we kind of just talked about if the retort temperature is higher, then retort time would be lower or less, and then vice versa.
Okay, so what if, for example, right now we have majority of the retort using 250 degree F. So what if we use 300 degree F? Can we reduce the retort time, right? So what do you think, why do you think we are not using that temperature?
Because it could be too high for the product. It could possibly alter some properties or maybe even like burn something inside.
Yes, exactly. And what else? Other people, do you guys have other thoughts?
It might be a temperature where, like, if you go any higher than that, it costs more money to heat than it's like worth, instead of like using like a rotational thing to like help heat up the item.
Good point, Lauren. So she brought up a very good point that if we use 300 degree F, then our cost of heating is much more, because think about the steam that we're using. The temperature is not as high. It's hard to heat food into 300 degree F using steam, right? We have to use other heating medium that will necessarily increase the cost. And also think about the cooling and the heating curve, right? If you use 300 degree F, that heating takes more time. The come up time is longer. So which means it's more difficult for us to control the processing, because under those heating and cooling curves, it's hard to predict their killing power, right? You guys did a lot of calculation in the lethality to last week, and during the heating and the cooling, it's the most unstable part of the in terms of their lethality. So that's probably another issue, right? So 250 is just another optimal point that we can balance the processing time and the cost and the stability of this process. Okay, so number 6, how about headspace, guys? So this is a pretty tough one. So we have Amy, Harmony, and Zoe.
Yeah, so we kind of talked about what Headspace is and why it's necessary, mainly to make sure that there's a good seal in the can, and also making sure that no oxidation occurs. And if you don't have the correct amount of headspace, like the food will spill out, or it's just like it will lead to like incorrect processing times. So yeah, the amount of headspace in a can affect like the cold point in the can, and alter that retort time. But yeah, it was kind of difficult to discuss. We weren't really sure what else, but yeah.
That's actually a good answer. And later on, we'll go through more in detail about headspace. So probably I should explain earlier that what is headspace, but I assume many of you can guess what it is, right? So headspace is the air, the amount of air that is above the food after we, for example, if we have a can, then we fill the food, right? But we leave some gap between the food layer and the lid. And that amount of air on the top is called headspace. And many research found that the amount of air we left there has a lot of impact on the food quality and their shelf life and also heat penetration. So we'll discuss about this later because this is one of the very tough point to think about without at this early stage of this class. Okay, so, but good job, guys. Number 7, we have Julia, Marley, and Misha. So you guys talked about the ratio between liquid and particles. Whoever want to share?
So I go with like a lot of the things we've talked about previously. Basically, like the difference between trying to retort like tomato soup, like even though it is viscous, since it's like just a liquid, you would pretty much just get like the convection with it, and so you'd have like a quicker heat transfer. Whereas like if you have something that's very chunky, like a chili, or I don't know, another like the Chef Boyardee example, you would get more conduction, and like it would just be more difficult to like get everything up to an even temperature, and so you'd like really have to take the time to make sure that happened.
Good discussion. Other groups, do you guys have other points to add? Okay, I think group 7 has covered pretty good about this idea. Well, so the last one, pouch versus can. So this is probably another tricky one. So we have Emma, Jackson, and Michaela.
So we talked a little bit about how the pouch would, for one, have like a reduced cooking time, and also would most likely be able to fit like within the package more like evenly, spread out more evenly, so it cook more like throughout, compared to a can, which might have like some overcooked on the edges and like undercooked in some spots.
Good point, Jackson. So this is probably one of the tough one, and I think the group 8 has mentioned a very good point about the heat penetration in pouch might be better because the package is more flexible, right? So any other thoughts do you guys have? So pouch processing is kind of a new idea which developed in the past 10 to 20 years, right? So because it's more light and the packaging is more, especially I think for military purpose, the pouch is more feasible, right? We don't need a can opener to open it, which can save a lot of space. So, but comparing them, it's quite difficult, and that's part of the assignment that I will give you guys after the sterilization topic to explore more about the pouch and can. How are they different in terms of the process design and you know, how to select the good pouch material. Okay, so that's it for the discussion. I think all of you guys did a pretty good job. Okay, so I will go through some of those factors in this class, and for some factors like packaging effect, I will leave that as a homework to you guys. Okay, so first one is the viscosity. As group one already mentioned, the viscosity actually impact the cold point, right? So we briefly talk about the cold point in the thermal processing principles. And here just want to give you a quick review. So cold point is the slowest point that when we heat up foods. If we have liquid food, then we have more convection, okay? And which the convection means the content in a can, it can move freely due to the density change, because when we heat up those liquid, those hot foods or hot liquid moves to the top due to the less density, right? So this is how they move, right? So basically they form a recycling of the moving, and the cold point in this case is slightly lower than the center, depending on how viscous it is. Okay, so typically if we're talking about a water or something that is not viscous at all, and then the viscosity is probably around 1/4 of the height from the bottom. Okay, and in some cases it can be 1/3 of the height, so it really depends on the viscosity. But in other case, if we are using a highly viscous foods, and then the viscosity will make the convection impossible, and the only thing happening is the conduction. In that case, the cold point will be in the center. Okay? So so in this case, we have to put our thermocouple in the center to monitor the cold point temperature. Okay, so this is a very quick review in case you are not familiar with those two concepts. Okay, so think about different types of foods. So for example, if we use apple juice, or some case we have discrete particles in liquid, for example, peas. In that case, the convection is happening, and we have the cold point in the 1/4 height of the liquid. Okay, and in other case, if we have highly viscous food or highly matted food. So matted food is something like we have a flat sides, or like they spread horizontally in the can. For example, spinach, those leafy greens, or sometimes pumpkin. If they distribute it in that way, then they kind of block the convection, the vertical movement of the liquid. In that case, although they are not that viscous, but their convection is kind of hindered, right? So in that case, we will have the cold point in the geocenter of those cans. And sometimes we even have some combination case. For example, if we have particles in the viscous liquid, but not that viscous, for example, the cream style of corn, in that case, we have the combination of conduction and convection, but the convection is not a very it's not very extensive. In that case, the cold point will be slightly lower than the geocenter, but not as low as the 1/4, where the case for the water or other non-viscous foods. So those are three scenarios that we have depending on type of foods. So we use a thermocouple, okay, to monitor the temperature at the cold point. And this is thermocouple. The left one is the thermocouple that we'll use tomorrow. Okay, that's the one that we have. So basically, you can see there are two windows on the thermocouple. They are used to transform the data between the thermocouple and the interface. And because it can tolerate ultra high temperature and the moist, so those thermocouples are quite expensive. To my experience, we have the data trace from Mesa Lab can cost more than $1,000, and because they store data by battery, the battery has to be specialized as well. So the battery here, we used to purchase like 10 batteries, so they cost like $200. So quite expensive, okay? So here in this experiment, if we want to figure out the cold point, we need to place the thermocouple to different location, right? So for example, the close to the bottom or close to the center. So in our lab tomorrow, we'll also use a thermocouple to monitor temperature at two locations of the can. But in our case, we cannot freely adjust where we want to place the can, because there are two ways that we can adjust height. One is use a screw. Another way is that we kind of open a hole on the top, and then there's a rubber that can help to fix the probe to different height that we want. But we don't have that adapter. So in our case, we have to, I will talk to you later in the lab, in the lab design, we have to control the headspace to, to change the height. Okay, so I think we have two chat boxes. Okay. Okay, thank you, Dr. Lammert. She said she wants to go. Okay, so thank you for coming. Well, so let's continue this topic. So here I want to show you a few plots that we got from our previous study about those different locations in the can, how they can impact the heat penetration, how the temperature is so heterogeneously distributed in the can. For example, so for when we're processing the tomato juice, and we place the thermocouple into three different spots into a can, 3/4 of height, and 1/2 of height, and 1/4 of height. And the thing about the tomato juice is not that viscous, right? So the cold point is more close to the 1/4 of height. And you can see that their heat penetration curve are so different, right? If we monitor temperature at the center, then probably we'll under-process this product at the cold point and cause a lot of safety issues. So that's how important it's of cold point. Okay. So that's the convection case. And if you think about more viscous foods, and this is something we call the matted food products like spinach, leafy greens, since their leaf can block the conduction, the convection, the movement of water vertically. And you can see that if we compare the temperature between the center, which is 1/2 of the height, and the 1/4 of height of from the bottom, they're also the center, the cold point in the center, it's much slower, right, in terms of heating process. So that's the case that we have hindered convection and only conduction happens. Okay, so they are very, very different. Okay, and here we are comparing different can size. Okay, so for example, if we compare number 2 can and the number 10 can, and you can see that because we know number 10 can is slightly larger than number 2 can, there's a standard chart of the can size that you can find. I'll probably upload that table to the canvas for your reference. So if you need to find a size for a certain size of number of can, you can locate that in that table. So we know that. So we know that number 10 can is much bigger than number 2 can, and you can see that for number 2 can, if we heat it up in a steel retort for 120 minutes, we can reach the optimal temperature. But if we processing a number 10 can, even after 3 hours, and you can see we start even at high temperature. After 3 hours, the cold point is still below the retort temperature. Okay, so with larger can, we have to add a whole lot more time, maybe several times more time. So it's also a big difference in terms of can size, right? Very different. So this chart actually compares the difference between steel retort and the rotary retort. So steel retort, the later one is like a brand name of a FMC retort company. The retort that they put, because they kind of occupy the majority of rotary retort market. So a lot of cases people use steel retort to represent the rotary retort. So when you see the steel retort, you can just regard it as one type of rotary retort. Okay, so in this study we compare the tomato juice in steel retort and the steel retort, and you can see that the steel retort actually saved much more time in terms of the processing, right? It takes less than 10 minutes to reach to 250 degree F, but for the steel retort, it takes almost 45 minutes to reach the processing temperature. Okay, so impact of headspace. So this is another very complicated topic, right? So a lot of research has been done to study the impact of headspace, and here I want to show you one example how what people found. So in this study, they actually controlled the headspace by the filling weight. Okay, so the x-axis here is the filling weight. So if you see a smaller filling weight here, that means a larger headspace. Okay, so the y-axis is the headspace. Okay, it's in the volume, in the unit of volume. So larger headspace, smaller filling weight. Okay, and so they control the filling weight from 480 gram to 510 grams. So we can change, we can vary the headspace from 16 what's the volume in the inch. I think it's cubic inch, something like that, and whatever. So the headspace range from 16 to about 6. So when we process them, actually we can achieve quite different F value. So remember, F value is how many it's kind of for example, if we talk about 3 minutes for the Clostridium botulinum, that's like 12 D reduction, right? So if we have F value is 6 minutes, then we're talking about 24 reduction of the Clostridium botulinum. So this is F value is just to an indicator here to show how many log reduction that we have achieved, and it's written in the in the unit of minute, right? So the higher value means the more heat penetration and the more log reductions. And the x-axis is the heat, the field weight, right? So if you look at the 480 field weight, which means we have a lot of headspace, right? So in this case, you can see that we reached a much higher F value. Okay, so that is also related to the rotation speed. So in the first curve, the highest curve, we have the rotation speed 10.6 RPM, and combining with the most headspace, and we can actually achieve the highest F value, which means more log reduction. But if we reduce the rotation speed to 5 RPM, then in this case, the headspace doesn't change does not necessarily change any significant difference in terms of the F value, right? So if we think about, so this study shows that headspace has to be combined with the rotation speed to make impact on the sterilization value, which is the F value, right? So if we only control the headspace and use a very low speed, then probably we cannot increase the F value. But only if we using a certain amount of rotation speed plus a certain amount of headspace, then we can increase the F value. So it's quite complex situation, right, guys? Is that clear, guys? Okay. So this is something that I hope I will leave a homework about those free exploratory assignments that you guys can look into those literature and think about more. So this is just to give you one example about how complicated situation is. And we haven't even considered what type of food, what viscosity we're dealing with, what is the shape of a can that we're dealing with. So if we bring that factors into account, then the scenario gets a whole lot more complicated, right? So a lot of things to discuss in that case. Okay, so finally, before we finish, we'll quickly go through a few retort systems. For example, the steel retort, it looks like this, quite old-fashioned, and it's really used now because it takes a long time. As you can see that it takes 3-4 times longer than the rotary retort to finish the process, to heat it up, right? So it looks very simple, and it's not used quite often now. So right now we use more of the rotary retort or agitating retort. So this is also another batch processing, but it's not a steel processing, it's shaking. So that's the one that we have in our pilot plant. It is a agitating retort. Basically, we are adding the shaking to force the convection to occur. That will increase the heat transfer rate. So for the rotary retort, that's the one we always talk about, the stir retort. Okay, so we have those retort cans on the side of those rotary motor. Okay, and we are rotating them at a certain RPM, or they are either shaked in under a certain degree of the depending on the system design. Okay, but the problem is that you can see we can only process a few numbers of cans because we're kind of wasting a lot of space here, right? It's a quite big chamber, but we can only place, maybe utilize 10% of the volume in the chamber. But if we use shaking, agitating retort or steel retort, we can fill the entire chamber with cans. So that's one of the limitation of the rotary retort. And the last retort system that I want to share with you is the continuous retort. So if you think about a continuous retort, it's quite difficult, right? Because if you look at the figure, the pressure inside is so much higher. And if you want to open an entrance and exit, that will actually, the inside, the pressure will vent through those entrances and exit when you want to bring in the can and export the can, right? So it's not easy to actually put those cans into a pressurized system. So here I want to share with you one system that a company designed. I think JBT designed this system. It's called Hydrostatic Retorts. Basically, they're using water to control the pressure. And this figure is the overall diagram of this system. But let me show you a video, so probably you will have a better idea about how this system looks like. So this is the hydrostatic sterilizer that JBT has designed. And you can see that there are 3 regions. On the, so if you look at the top, there maybe there are better one. Let me see. Okay, so this is how it looks like. So we have a feeding system. It's like conveyors, and it's a long process. And inside, you can see here, all the cans, they are shaped into a certain angle to be feed into this system. And each can has a like a fixer to kind of making sure it's not moving inside the system. Okay, and once it's feeded into the system, we have several different regions, right? The first one is called preheating. Okay, so in this part, it's actually filled with water. Okay, and so we use water to heat them up. And once it's heated up in the sterilization system, the temperature is already brought up to the standard temperature. And if you look at this figure, you'll see that because we know that inside this chamber, the temperature is about 250. So the pressure is much higher than the atmospheric pressure. So the way that they control the pressure is to use water. So basically you can see the water level on the left is in the preheating area is much higher than this pressurized area, right? So that's actually adding the pressure. And also we have a steam valve here to add steam to pressurize this system, right? So inside this chamber, we actually use the water to control the pressure. And if we want to increase the pressure, we can easily accomplish that by increase the water level on the left side, right? So the pressure can be so easily adjusted by doing so. So, and on the left side, you can see the water is cooling down by spraying to the top as a water shower. So the water has several different roles they are playing in this system, right? So first of all, they're heating the cans in the preheating section, right, as a heating media. And the second, we use the difference of the water height to control the pressure. So second, they are a pressure moderator, right? And third, the water in the steam is another heating media in the sterilization region, right? And finally, we use water to cool it down. So everything is controlled by water, right? So that's and because all the water is they are not contaminated at all, so we can simply reuse them. So this is a very genius design by the JBT. Any questions about the hydrostatic sterilizer? Okay, so this is one design of the continuous retort system. Okay. So in continuous processing, we can maintain the pressure and temperature and the residence time by, residence time. The residence time can be controlled by the time of conveyor moving, right? And but the problem is that the can size and the shape is not flexible, which means if we want to process a larger can, we have to replace the entire wheel, and that will cost a lot of money. So that's the one of the drawback, and also the investment will be larger as well. So finally, before we finish, we'll quickly go through the tomorrow's lab. So tomorrow we'll process two types of foods. One is refried beans, another one is the green beans. Okay, so refried beans is one of the viscous food, and the green bean is the one of the non-viscous food, but with more convection occurring. So we'll place because we cannot move our probe thermocouple inside the can, but we want to control move around the spot of probing. So what we'll do is that group one, you guys will put the probe on the bottom, okay, and fill the can. So the probe will be about in the center or 2/3 or 1/4 between that 1/4 of the height. It'll be more close to cold point. And group two will leave the probe on the top. So, and because we have some head space between the lid and the sample, so in this case, our temperature that we're probing might be more further far from the cold point. Okay, so for group three, you guys will do the same thing, but you guys will processing the green beans. Okay, so and each group will prepare two cans. We'll use another can as a control to monitor the color change before and after. Okay, so one thing that I want you guys to record or measure is the height of your probe. Okay, so after before you fill it, please measure what is the height that you're probing. Okay, and also please measure the overall height that you're filling the can. Okay, so that's all that I want you guys to record. And after tomorrow's lab, we'll gather the data from Molly, and we will do a lot of calculation on the class next week. Okay. So is that clear, guys? It should be a very simple one.
Sorry.
Go ahead, guys.
I just know a couple of us are confused who are in the virtual lab. So are we supposed to log on to Zoom, or you were saying that it's all going to be recorded and then put up a day later?
We will record the video and upload that.
Okay, cool. Thank you.
Yeah. So for this lab, one thing I have to mention is that it's a quite boring lab, because once you guys prepare can and put them into the retort, it's almost 2 hours and more of waiting time. And normally in the 204 class, we let students go. But in this class, after talking with Molly, she felt bad with running, everything by herself, because, waiting is part of, the lab, and certainly we can discuss some of the topics during while we're waiting. So guys, please don't leave, and we'll just, probably we'll talk about some, the retort system, and I will bring up a few topics that we can go through while we're waiting. But please expect this will be a slightly longer of waiting time. So just want to give you a heads up. Okay. So a few points that we have talked about today. First, we kind of review the purpose and principle of sterilization process. Second, we talk about the different factors affecting survival of growth of microorganism, the pH and the water activity, right? And third, we identify the heat transfer types and how to find the cold point. And also, we discuss a lot about those key factors affecting sterilization. And finally, different retort systems, right? The still retort, rotary retort, and the continuous retort. So do you guys have any questions? Any questions before we finish? Okay, good. So I'll see some of you tomorrow, and we'll try to upload the video as soon as we can. So for this class, I will give you every group 2 weeks to write a report. For example, so our lab is tomorrow, so the report will be due 2 weeks from tomorrow's lab. Okay, so there will be plenty of time for you to discuss and compose a lab report. Sounds good? Okay. All right. I'll see you tomorrow and maybe some of you next week then. Thank you, guys.
Thank you.